Good morning, I'm Franco Angelini from University of Pisa, and the title of this talk is Trajectory Tracking for Articulated Soft Robots, an Iterative Learning Approach. Articulated soft robots are systems presenting lumped elasticity at the joints. These compliant elements allows them to behave safely and robustly. Controlling soft robots is not a trivial task because their dynamics is typically hard to model, and then we have that feedback controller increases the stiffness. So for example, in this experiment, you can see how a compliant robot behaves as stiff when controlled with a feedback controller. So our solution is to design a model-free feed-forward approach, in particular a learning-based method. The control framework we propose is based on iterative learning control, and it presents an initial guess, control gains to update the control action based on the error of the previous iteration, and finally a very small feedback terms. And this feedback terms is small to avoid any stiffness alteration. As you can see in this experiment, the robot at the beginning is not able to perform a task that is basically a rest-to-rest task through two obstacles. Then, through repetition of the same task, it is able to achieve the desired tracking performance. However, controller based on iterative learning control presents some generalization issues. And in particular, we have that the acquired control action depends on the learner stiffness profile, the learned trajectory velocity, and finally on the trajectory itself. So we developed techniques to generalize with respect to these parameters. Let me start with the stiffness profile. To tackle this issue, we simply exploited some property of the system. In particular, from this control input, we decouple the dynamics of our system in two separate parts with two separate inputs. In this case, we can learn the motion of the link while using a different controller to track the desired stiffness profile. In this experiment, you can see that with only one learning process, we can track the same trajectory with different stiffness profiles. Moving on, generalization with respect to time. In this case, we would like to track the same trajectory with slower motion and also with faster motion. So basically executing a time scaling of the trajectory. In this case, the solution is that we need 5 different examples of learner control input with 5 different velocities. Skipping the map, I will just show you the results. In this case, we can acquire 5 different examples and then we can generalize. Finally, for what concerns the generalization with respect to the trajectory, we can exploit the Gaussian process regression to create a map between the desired output and the input. In this case, we use the map to generate another control action for another desired output. And we have that if this novel desired output is similar to a previously seen example, the learning performance will be much faster. To conclude, I presented a control framework for trajectory tracking with articulated soft robots. This control framework is based on iterative learning control. It is model-free and it is able to preserve the compliance of the system. I also presented techniques to generalize the previously acquired control action, in particular with respect to stiffness, time, and also space. Future work will focus on the generalization with respect to the payload and also the application of this control framework to a real industrial context. Thank you very much for your attention. If you have any question, please contact me.